Hi everyone, my name is Kevin, and I was a part of the 2025 risk cohort. In this video, I'll be presenting my work from the summer on responsible autonomous driving. With the deployment of autonomous vehicles at scale in 2025 and beyond, ensuring their safety and efficiency has become more crucial than ever. However, this remains an open research question. Autonomous driving is difficult because decision-making hinges on various factors, many of which are context-dependent. This means that trajectories can't simply be pre-computed offline. We can't simply plan for everything that could possibly happen while we're driving. For example, depending on traffic density and road geometry, a car may have more or less room to move around. Take for instance the two images on the screen. In the left image, a car is driving on an empty highway and it has much more room to navigate between lanes than the POV car in the right image, which is driving in a packed highway. Driving is also fundamentally an interactive task that requires implicit coordination, because each vehicle can't perfectly observe what other vehicles are thinking. As humans, we use cues to communicate our own intention and understand those of others. Autonomous vehicles must effectively manage intention uncertainties to behave in a safe and efficient way. To my last point, driving is difficult because it involves optimizing both task and safety objectives, which often conflict with each other. In our project, we focus specifically on inter-vehicle safety, which is collision avoidance between vehicles. The existing works can be categorized somewhat into two different classes: reachability-based and responsibility-based safe control. Reachability-based safe control considers the physical limits of vehicles. Given my current state, what states can I possibly reach? A common approach in this class of works is to first predict a set of plausible future human states using a motion prediction module. Label this set as the failure set and perform collision avoidance to avoid any failure states. While these approaches are able to achieve safety assurances, they make worst-case assumptions about other drivers, which leads to over-conservative robot behavior. Responsibility-based safe control is a recent idea that facilitates reasoning about safety in a more collective way. Asks the question of what proportion of effort each individual agent should put towards collective safety. A common approach to allocate is to first allocate responsibilities using a function, which can be either hand designed or learned from data, and plug the outputs of this function, which are responsibility shares, into a safety filter. Existing works have explored allocating responsibilities using social or state-based considerations and are able to relax worst-case assumptions about other agents. However, they assume that other agents' intentions are known, which is not true in practice. Furthermore, these works only consider whether an agent is either able or willing, whereas responsibilities in real life depend on both. To address these limitations, our project contributes the following. A new formulation of responsibility that accounts for an agent's ability and willingness. A set of axioms that ground our responsibility formulation to intuitions. An uncertainty-aware framework to compute responsibilities from observations of human behavior. And probabilistic safety guarantees, which are regulated by the designer's specified hyperparameter. In our work, we design a responsibility allocation function to consider whether an agent is both able and willing to contribute to collective safety. In our project, we model safety using a control barrier function. The control barrier function, or CBF, is a safe control approach that has recently become popular because it is able to translate state-based safety specifications directly into actionable objectives. CBFs can provide rigorous safety guarantees by constraining the rate of change of a given safety value with respect to its quantity. Collisions between two vehicles can be expressed as a linear constraint considering the control inputs of both vehicles, and prior works introduced responsibility-aware CBFs as the product of partitioning the centralized constraint into two decentralized constraints, each which considers a single vehicle's control input. The right-hand side of this inequality can be interpreted as the amount of effort that each individual agent is expected to put. This amount of effort is a function of an agent's responsibility share, as well as the total amount of effort that the two agents are expected to put to maintain safety. The responsibility allocation problem poses the challenge of finding a function that can map agent states and other physical or social considerations, such as collision risk or social preferences, to pairwise responsibility shares, such that task and safety objectives are respected. As I mentioned, previous works design responsibility allocation functions to consider agents' social preferences, which are whether an agent is selfish or selfless, and state-based physical considerations. Specifically, the amount of collision risk that an agent is subjected to. However, these works only consider whether an agent is willing or able. We present our responsibility formulation on this slide, in which we consider an agent's context-dependent ability as well as its willingness. As done in previous work, we use social value orientation, a tool from social science, to represent an agent's willingness to contribute to collective safety. We formulate an agent's ability as the risk-weighted volume of the agent's feasible control space. Essentially, this measure considers the quality and quantity of motions that an agent can execute. By considering the quality of motions, we embed context-dependent collision risk into our ability measure. By considering the quantity, we embed context-independent physical limits as well. To systematically justify our approach, we present a set of axioms that help ground our responsibility formulation to human intuitions. These axioms help to demonstrate the social and physical implications of our formulation. To apply our responsibility formulation, we present a three-step responsible driving framework, in which the robot first infers how safely a nearby human is driving. Based on this inference, the robot can then select its own responsibility share, and then it can apply a responsibility-aware safety filter to ensure that it's driving safely. The first step in our pipeline is to infer a nearby human's driving style. We model the human's decision-making with a reward function that is separated into task and safety-based considerations. We model the human's safety decision-making with a hinge CBF cost. Essentially, this evaluates how safe a particular action is at a particular state. We want to infer two different parameters, being one, a coefficient that describes how well our model describes the human's driving style, and two, the human's social value orientation, which describes how responsibly they're driving. The first parameter enhances robustness to potential modeling errors. Based on the inferred parameters mentioned on the previous slide, the robot selects its own safety strategy to match the human safety strategy. We compute a point estimate that embeds uncertainty from both belief parameters into a single value. In turn, the robot can use this to directly select its own responsibility share. The last step is to apply a responsibility-aware safety filter. We define safety using a distance space value function, and we can perform safe control by embedding the CBF into a quadratic program, which is a common strategy used to translate safety specifications into safe actions. Future work will include performing extensive evaluation to demonstrate our approach's effectiveness. We plan on testing in multiple scenarios, such as highway ramp merging and traffic intersections. We will compare to both responsibility-based and reachability-based safe control approaches. When comparing to the latter, we hope to show the effectiveness in reasoning about uncertain human intentions. We plan on comparing to existing approaches that don't reason about human intentions, such as a collision risk-based allocation of responsibilities, which was proposed in prior work, as well as 3 static responsibility baselines. We plan on comparing to reachability-based safe control approaches as well to demonstrate the effectiveness of relaxing worst-case assumptions about other drivers. We will use a collection of objective and subjective metrics to evaluate our approach. We will measure the vehicle's safety margins over time to evaluate our approach's ability to maintain safety. We will use completion time as well as deviation from nominal controls to evaluate task performance. Through these objective metrics, we hope to show that our approach achieves a better balance of task and safety considerations. We will also use subjective metrics to demonstrate that our approach can infer a human's driving strategy in an interpretable way. Future work will include exploring how to obtain both safe and unsafe data so as to properly infer human safety strategies. We also plan on exploring how to include this full circle of social value orientation values, which is used in social science, and scaling the number of agents in our tests. This concludes my video presentation. I would like to thank my mentors, Iwei and John, for not only this great opportunity, but also their patience and guidance throughout the summer. I'd also like to thank Rachel Burson for making RIS possible and my fellow RIS cohort members for making the summer so memorable. Thank you for listening to my presentation.